Apparently people aren't too worried about
What?
this class.
No. With the amount of people that are here.
Yeah.
It's like, yeah, I got it.
Yeah, out of a class size of
It's
what,
like, what, there's like 8
130?
people here?
Yeah,
No, 11?
because this is like, you can take this after just MEB, right? So.
Okay.
Sweet.
So basically, this is an engineering class, which means it's heavily based on calculations. So in this review, I will review those questions that require calculations, and will mention some points might be helpful in the exam. But so in the exam, I got the question. Just a tip, it has like true and false questions, as Dr. Jiang mentioned in the class, and several calculation questions. For the true and false, I checked they're all in the slides. So if you guys look at the slides carefully, you will get all those correct.
Your slides?
No, in the lecture
Lecture
slides.
slides.
Yeah, because there's some questions is like in the background information, conceptual questions, so I won't cover here.
Can we have like
Well,
one
I would-
example? Like what? I mean, not like one from the exam, but is it like what is
Yeah,
is
what-
carburization the process of blank, and you say true or false, or like?
Like, suppose for here, I could make a true or false question, means, so a material will first go through plastic deformation, then elastic deformation.
Okay.
False.
That's a false, right?
Mhm.
Because you go through elastic first and then plastic. Okay, so here I will review from chapter 6 because this one is like the most important chapter in the whole book. And that's basically the pure material, the material properties are all covered in these chapters. So first, we have these two concepts. One is elastic deformation and one is plastic deformation. So elastic means when you deform the materials, when you release the force, it will back to its original state, but not for the plastic. So here, how we quantify those material properties? We use one thing called engineering stress and one thing called engineering strain. So the stress, before I go into this, I will remind you guys, pay attention to those equations because this is engineering class. You will require to calculate something. How do you calculate something? Those things are all from the equations. So if I were you, I would just write down all the equations I met in this class and finish it. So, and the second thing to do is to understand what's the variables in the equation. So this engineering stress is defined by the force divided by the area. The area, you need to pay attention here. The area where is not the area that is instant. So the area one. So when you define a material, it will get thinner, obvious, because you need the conservation of the volume and the mass. So the area will get thinner. But here the engineering stress is defined by the original cross-sectional area. So, and the engineering strain is defined by the change of the length divided by the original length. So here should be around the 0 here. Okay, and based on these two, the stress and strain, we can get elasticity modulus called Young's modulus. This modulus will describe how the material can deform. You see, with the higher bonding strength, which means the bond between the metals will become strong. They are hard to deform, so they will have the higher modulus of the elasticity. And so from this curve, we can see here, in this region, you can see the mouse, will be the elastic deformations, which characterized by a straight line, with the slope is the Young's modulus. And here it starts to perform as a plastic material. So we need to define a yield strength. What's a yield strength? It's actually a stress. How do we get this stress? So we first move from like 0.2% here to the strain, and we draw a line. The intersection would be the stress, which we call it yield strength. So this definition is based on the US, but as you guys know in the class, it's different like anywhere else. Okay, and there's another quality called ultimate tensile strength. So when you keep stretching material, it will finally to one point that it can hold the maximum stress. So this is the point. You can see a plateau here, which is the maximum stress. So that point we define it as the necking point, and the stress is the ultimate tensile strength. Okay, so now let me see. What we're talking is called engineering stress. We define it because it's easier for calculations, but in the real world it is not, because when you stretch the material, the cross-sectional area will decrease. So here, the true stress will equal to the force divided by the true area at that time. And the true strain, you can, it's this equation. If you want, you can like integrate it, but just remember the simplest form. And you should remember that the true stress is always greater than the engineering stress, because the area, they will only decrease, they won't increase. Okay. So for the material, we need a value to quantify how the material can deform under easier to deform under the stress. It's called the ductility. And in order to quantify these data, we use a thing called elongation. So for this, you guys already see this for the homework. Just remember, it's the change divided by the initial length. That's compared. It's always compared to the initial. It won't compare to the final length. For this reduction area too, so it's the initial area minus the final area divided by the initial area. So here you guys might want to go home and do an exercise to compare the relationship between the true stress and the engineering stress, or the true stress to the true strain to the engineering strain. So you guys must know the difference between these two, because they will have you will meet this kind of problems today after tomorrow. So here it's a simple question from the book. Just show what's the difference between the engineering stress and the true stress and strain. So we can see here. You guys need to know the equations. So because the exam, the question won't be just like this, just like as you plug in the numbers. It might be some deviations as you convert these manipulate these equations to calculate something. So you guys first need to be very familiar with these equations. You must know like what's the engineering stress, what's the true stress, like what's the difference. Okay, this is basically chapter 6. It's like, if you guys have anything about the concept, you can ask me right now. I can explain to you the stress and strain. But basically, what we test for now is information to here. So basically, you guys just a quick review. You guys need to know what's the engineering stress, what's the engineering strain, what's the Young's modulus, what's the true strain, what's the true stress, and what's the yield strength, and how to calculate this percent elongation and percent reduction in area. Okay, now we're going to chapter 3. So among these 4 chapters, you can see chapter 6 is the most important one, and then chapter 3 and chapter 5. As you guys might know, for the quiz tool, you don't have questions in the chapter 4. That maybe tell you that chapter 4 is not so important. But it is important because there will be some small points there. But I suppose you guys, if you have limited time, focus on those 3 chapters first. So in chapter 3, what do we learn? We learn the basic of, we learn the material in the atomic section, atomic level. So how do a small unit qubit cell form a large material? How this small unit contribute to the material properties of a large material. So basically, we talk about, I think, 12 different qubits, but there are 4, Dr. Jiang mentioned, will be the most important qubits. One is the simple qubit, the body center qubit, and the phase center qubit, and the HCP. So for these 4, there are like basics you need to know. One, it's all summarized on this slide. One is you need to know how many atoms in each unit. So as you guys might see, if the atoms on this corner, it will be 1/8. If on the face, it will be 1/2. It's in the center, it's 1. So you guys need to know this. And another thing is what's the relationship between the A and the R. The A is the qubit length and the R is the diameter of the sphere inside. So for this, I think it's like summarized in the slide. You guys can like just write it down and take it to the exam. If you you want to try, you can derive by yourself.
Could you do the HCP one? I'm curious to see how you would do that.
So that's really, so if we have time.
If we have time, okay.
So basically, if you look at the notes I upload, so I upload so in HPC there are 3 relations. So you have the A and you have the C. So C is the length. Okay. So based on each material, they will tell you different what's the ratio between C and the length. But still from this, you would you can find this really easy. I can show you. I'll show you later.
Okay.
So, but I won't do it for you because I say this will focus on homework and quiz. If you guys happen to ask some questions in the exam, I won't be able to answer it. So in this case, I won't answer any other questions like not from the homework and the quiz. Okay, you understand the logic?
Oh, I don't think we had to calculate HCP from the homeworks.
Right. So.
Oh, so that's what. Okay, so you're not getting into that because it's not on homework. All right,
But if you look at the things I upload a figure that's like tell you exactly
Oh, okay.
the relation between A and R.
Thanks.
And also, this is very important is atomic packing factors. So it tells you the efficiency of about kind of packing. So this you should know what's for the single qubit, what's for the HCP, what's for the FCC, and what's for the BCC. I think it's all listed. Okay, that's the importance